Okay, so let me remind you where we were. So we are looking at the two algebras that will be the final ones, the one that actually work. Cu and Qu. And Cu is a Lie algebra given by the commutation relations written here. I'm just going quickly over what we did last time. Sorry, not Cu. SL2 plus epsilon is a Lie algebra. Cu is the universal enveloping algebra of this algebra with a given structure. So basically with antipode and coproduct defined by this. You know, last time I went through it quickly, and in fact I'm planning to go through it even quicker now, but perhaps I should have explained why this structure makes sense. Okay? So, well, so the coproduct, let's mention the antipode later, but the coproduct is defined on the generators, and I plan this to be a Hopf algebra, or I'm defining it as a Hopf algebra, so the coproduct should be compatible with the product. So basically, applying the coproduct to a product is the product of the coproducts. So, so it's enough to define the coproduct on the generators. This defines it on the rest of the algebra, on the rest of Cu as well. But there is still one thing to check. I mean, Cu is a universal enveloping algebra, which means it's not just generators, it's generators modulo relations. So we have to check that the coproduct is well defined modulo the relations. And this I didn't do last time, and maybe it's worth doing now. So I'll make it a general statement. So if you have U being the universal enveloping algebra of some Lie algebra, which means that it's just words, or it's the free associative algebra generated by that vector space, so basically arbitrary words, modulo the relation xy minus yx is equal to x bracket y, so two-letter word minus a two-letter word is equal to a one-letter word. And you can always define a coproduct delta going from U into U tensor U by, so it's enough, as I said, to define it on the generators. So every x inside the Lie algebra just maps to x tensor 1 plus 1 tensor x, or as written here with this ijk notation, I mean, it's the same thing, okay? And the only thing I need to check is that delta is well defined. Well, not the only thing, but the main thing I need to check is that delta is well defined. So I need to compute delta of a relation and shows that I get 0. Okay? So I need to compute delta of xy minus yx minus x bracket y, and here's what it is. Delta of xy is x tensor 1 plus 1 tensor x, so delta of a product is the product of the deltas. So delta of x is x tensor 1 plus 1 tensor x, minus, times the same thing for y. So y tensor 1 plus 1 tensor y minus the same thing in the opposite order. So y tensor 1 plus y, plus 1 tensor y times x tensor 1 plus 1 tensor x minus x bracket y is a single letter. It's a single generator. So coproduct applying to x bracket y is just x bracket y tensor 1 plus 1 tensor x bracket y, except that there was a minus in front, so I wrote this plus as a minus. Okay? And now you can just carry out the multiplication. And over here, you will get x tensor y. Not x tensor y. xy times 1. So xy tensor 1 plus x tensor y from this and this. So plus x tensor y plus from here and here you get y tensor, right? 1 times y in the first factor and x times 1 in the second factor. So it's y tensor x. And from this and this you get 1 tensor xy. From this I'm subtracting that. And this comes out y tensor x minus this and that is y, this and that is y times x tensor 1. So yx tensor 1. This and that is y tensor x. This and that is x tensor y. And this and that is 1 times yx. And from this I'm subtracting this. So xy tensor 1 minus 1 tensor xy. And now x tensor y cancels x tensor y tensor x cancels y tensor x. These two pack together to, in fact, these three. This, and that. So three things taken together all of them have 1 on the right tensor factor. So this is xy minus yx minus x bracket y tensor 1 plus now this one and this one all have 1s on the left tensor factor. So plus 1 tensor xy minus yx minus x bracket y. And this is a relation in U, and this is a relation in U. So this is actually equal to 0 in U tensor U, which is what I wanted to show. You can similarly check that S is well defined, and then it's very easy to check all the properties. So the coproduct is co-associative, blah blah blah. Everything is automatic. This is the only hard check. Okay. Yeah, I should have done it last time, but I didn't. I'll explain in a moment why. Anyway, next. So the next algebra is QU, and again I'm writing it here in full, and one has to check that all the properties are satisfied, and we'll talk about it maybe later. And Rij is the R matrix, the R element, and again it's given by specific formulas. And again, the convention is that I always order things in the order Y box. It's not important, but it's worth mentioning. And then come the big questions. So where is SL2 plus epsilon coming from? Why does it deserve the name that I gave it? How do we compute in CU and QU? Where does it come from? Where is the formula for R coming from? How do you compute with it? All of that. And at the end, did we succeed? Did we achieve the goal? And now I have to acknowledge that, well, yes, we achieved the goal, but not in this class. There just isn't enough time to finish going through all of this in what remains. I overestimated, and maybe even pushing to finish was a mistake because it meant not enjoying the way as much as we could have. So we'll get somewhere along here, but not quite finish it, and then maybe we will have a private discussions later about on how to finish it. But yeah, but we're not. So this is it, but we're not going to demonstrate it. We're going to go as far as we can. Anyway, I did mention the Pbw theorem last time. So basically, the algebra CU, being a universal enveloping algebra, is isomorphic to a polynomial algebra. Therefore, it's susceptible to the technique of generating functions. And then we had a proposition saying that the generating functions for all the pieces of the structure are given by the explicit formulas written here. And I want to go over these formulas, and especially the weird formula at the end. Okay? So, okay, so maybe I'll first explain the notation. So you see, I mean, these things are more than just generating functions, are elements in a category. Okay? So I've indicated it as follows. So when I write C eta I, so C stands for, it's the eta, the unit of the C algebra. There will later be a Q eta I as well. So C eta I is the element in the category of generating functions, which goes from the empty set. You know what? Maybe it's more fun to go with delta, because delta actually has both inputs and outputs. So C delta ijk is the element in the category of generating set functions, which goes from I to jk. But again, our algebra really has 4 generators, y, b, a, and x. So what I really mean is that it's going to be a generating function with Greek letters corresponding to I and Latin letters corresponding to j and k. So it should have an eta I, a beta I, an alpha I, and a psi I, and outputs yj, bj, aj, xj, and likewise with k. Okay? And then I claim that this generating function is, so when I write E stands for exponentiation. So the generating function is the exponential of what is written here within the brackets. Okay? So let's check it. what is the generating function of delta ijk? So by definition, or not by definition, but we checked that the generating function of any linear map is equal to the linear map applied to the exponential of sum of zeta I zi, where I runs on over all the input variables. So for us, this should be delta ijk applied to e to the so the input variables are y, b, a, and x. So it's eta I yi plus beta I bi plus alpha I ai plus psi I xi. Now, this is multiplicative, so this is equal to the so basically delta of an exponential is the exponential of the delta. Okay, so this is e to the delta ijk of eta I yi plus all the way up to psi I xi. Again, if you have a multiplicative map, if you have a homomorphism, so basically if L is a multiplicative map, then L of e to the x is e to the L of x, because e to the x is just sum of x to the n divided by n factorial, and L threads, I mean L, well, I think it's enough. Anyway, but delta ijk acts on the yi and gives yj plus yk. So you get e times eta I yj plus yk plus ta up to psi I xj plus xk, because that's what delta does. It replaces each variable by each generator zi by zj plus zk. So that's what you get. But this is what I call e of the same quantity, and then I just annotate it with the domain and range as written here. So so I've done it for the most complicated one, and you can check that all the others are easier, except for multiplication. So classical multiplication, so the generating function of the classical multiplication with input ij and with output cm, well, I don't know what it's going to be, but let's just think about it. It should be, well, I'm asserting that it's the exponential of something. The inputs are I and j, which really means Greek letters eta I up to psi k, and up to psi j, and outputs yk, ak, bk, and xk. So output Latin letters with indexes k. And then I think I claim that the generating function is e to the lambda, where lambda is given by this lovely formula. Okay? So just if you look at this formula, it has the right shape, right? It has Greek letters with I and J, and Latin letters with K. Okay? Maybe before giving you half a proof, I'll tell you that I have no emotional attachment to this formula whatsoever. I mean, I don't think I've even typeset it myself once. It was generated by computer, including the typesetting. I mean, the formula really doesn't matter. What matters is how you get it. Okay? Okay. Anyway, so here's half a proof. So what we need to show is the following. So, so really, how do we, I mean, what is this generating function? Okay? So really, we have CUI tensor CUJ, and there is a multiplication map into CUK, but this is isomorphic via the ordering map. So there is an ordering map where you order the tensor factor I and j. This is isomorphic to the polynomial ring in variables in variables, you know what, I'll just write zeta I and zeta j, but what I mean by zeta is all of eta, beta, alpha, and psi. So really 8 variables. And this is isomorphic via the ordering map in tensor factor k to the ring of polynomials in zeta k. And then, so these two are isomorphisms. So if you do this composition, then you get a morphism here, and the generating function of this morphism is what I'm looking for. Okay? So, so how do I compute the generating function of this morphism? I evaluate it on e to the eta I yi plus all the way up to psi j xj. So this is a sum of a thing. And it should come out, I assert it comes out to be e to the lambda. Right? So I need to compute, so if I don't want to invert maps, then I need to compute that if I apply Oij and then multiplication, I get O applied to e to the lambda. So that's the formula written here. I need to show that if you apply Oij and then multiplication to this, you get e to the lambda and then OK. Okay? Now, what is Oij applied, or what is this combination? So the combination appearing on the left is, okay, so first of all, I have to order, I have to take the ordering map and apply it to this. So this thing is really, the left-hand side is really at e to the eta I yi, e to the, right, I'm still in a commutative world, so it's e to the eta I yi, e to the beta I bi, e to the alpha I ai, e to the psi I xi. This is ordering, this is just equal. I mean, before applying the ordering map, I'm still in a commutative world. So the exponential of a sum is the product of the exponentials. So in fact, I can continue e to the eta j y j, you know what, e to the psi j xj. Now I order these things, which basically means that I put all the y's before all the b's, before all the a's, before all the x's. But that's exactly how I wrote it. So that's the do-nothing operation. So in the first tensor factor, I just get these. And in the second tensor factor, I get those. Okay? And then I apply the multiplication map. But what does the multiplication map do? It concatenates the two things. So basically, I get that. So the left-hand side just gives me this product. Sorry, but all of it now is happening in tensor, sorry. You know what? The multiplication map will map it, the only thing it does is that it changes the y's and the b's and the a's and the x's to all be in tensor factor k. Sorry, so the result is not what I wrote. It's not just deleting the tensor product. The result is e to the eta I y k, e to the beta I bk, up to e to the psi j xk. All of these now became non-commutative, and they are in the tensor factor k, number k. Okay? So, I need to check if this is equal to the right-hand side. What is the right-hand side? So let's write lambda as a product of, as a sum of four things. So it's a coefficient times yk. So let's call it lambda y yk plus lambda b bk plus so on. Sorry, lambda, yeah. Plus all the way to lambda x, xk. And then, again, this is still a, sorry, now I exponentiate lambda, and it's a commutative exponential. So I get e to the lambda y yk, e to the lambda b bk e to the lambda x xk, and then I apply the ordering map. But I wrote them in order, so applying the ordering map is the do-nothing thing. It's just replacing everything by hats. Okay? So I need to check an equality of two products of exponentials, and all of this is happening inside the universal enveloping algebra of our algebra. So you know what, I'll just write it as Cu in tensor factor k, and in fact with Greek letters added as coefficients. Okay, so this is 8 Greeks. Okay? How do I test a thing like that? So let me lie to you, or so far everything is good, but let me give you just half a proof. Okay? So the way you test one way to test an equality is to find a representation. So, and then apply the representation. Okay? So, definition, what's a representation of a Lie algebra? So a map rho from a Lie algebra into matrices is a representation if, well, so remember that matrices are themselves a Lie algebra by taking the commutator. The bracket becomes the commutator. So basically, is a representation if it is a morphism of Lie algebras, namely if it preserves the bracket. Namely, if rho of the bracket of x and y is the commutator of rho of x with rho of y, which just amounts to saying that it's rho of x, rho of y, minus rho of y, rho of x. Second, rho is called faithful if it is one-to-one. So if you find a faithful representation and you want to check an identity, you just apply the faithful representation and check if the identity is happening in n by n matrices. Okay? So we apply a faithful rho, and then it's a check in the world of matrices. And in the world of matrices, we know how to exponentiate, and we know how to multiply matrices. Sorry, I lied to you. It's not that we know. My computer knows. I don't know. If you'll ask me to exponentiate a 2 by 2 matrix, I'll panic and run away. Okay, but my computer knows how to do it. So here it is. Here is the representation. Y hat gets represented. I didn't even bother to call it rho. I just said y hat is the 2 by 2 matrix 0, 0, epsilon 0. B hat is this 2 by 2 matrix. So really I mean rho of B hat is this. Rho of A hat is this, rho of X hat is this. Now I need to check that it's a representation, so I need to check the commutation relations. So one of the commutation relations was that A bracket X is equal to X. So it means that I need to check that A hat dot X hat minus X hat dot A hat, dot means matrix multiplication. So I need to check that this matrix multiplication minus this matrix multiplication is equal to this matrix, and likewise for all other relations. And again, being a lazy bum, I just type everything in, hit enter, the computer outputs true, 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 and of course you could have checked it by hand, right? You could have just multiplied this matrix with this matrix, and you know, you could have checked it by hand, but the computer tells you that it's true. And then I need to check that this equality holds. But again, that's just an equality between, so a product of 8 exponentials is equal to the product of 4 exponentials. So since writing matrix X takes 1, 2, 3, 4, 5, 6, 9 characters, and that's too much for me, I define E to stand for matrix X, and then I compute the matrix exponential of eta I times Y times the matrix exponential of beta I times B. I'm dropping the K because they're all in tensor factor K, and I made the definitions without the K. So here is the product of the 8 exponentials of the left-hand side, and here is the product of the 4 exponentials of the right-hand side. So the exponential of y hat times what I called lambda y over there. But lambda y is just the derivative with respect to yk of lambda. Okay, because lambda is just a linear combination of the y's, of the variables. So the derivative with respect to yk of lambda is lambda y. So I just wrote del yk of lambda. Okay, I hit enter, and the computer says true, QED. Not QED, half QED. But before telling you why this is a half QED, I'll tell you that this is one place where I got very confused myself a few years ago when I first did it. So you see, oh no, even before that, sorry, even before that. I told you I'm not emotionally attached to this formula for lambda, okay? So let me tell you how I found it, okay? I found it by typing exactly the same thing, but instead of writing here delta yk of lambda, I wrote here lambda y, or lambda 1, okay? And here I wrote lambda 2, and here I wrote lambda 3, and here I wrote lambda 4. I actually don't remember what variable names I used, okay? But the point is that instead of thinking of it as a proof, I could use it to derive what are the lambdas. So if I write here lambda 1, lambda 2, lambda 3, lambda 4, the result is a 2 by 2 matrix whose entries, so if I compute it without knowing what the lambdas are, the result is a 2 by 2 matrix with entries, you know, functions of lambda. So e to the lambda 1 divided 1 over lambda 2, I don't know, I mean, functions of the lambdas. And the result on the left-hand side is some function, some matrix of functions of the Greek letters. So alpha 1 e to the beta, sorry, alpha I e to the beta j, I don't know, something. And then you get 4 unknowns, lambda 1 up to lambda 4, and 4 equations. This entry is equal to this entry is equal to that entry, and so on. And Mathematica has a built-in equation solver, so you type solve 4 equations for the 4 unknowns, and you get the formulas that I wrote. And then Mathematica has a built-in tech typesetter, so you typeset it straight out of the equation solver, and I've actually, you know, I genuinely have never typed these solutions. I really don't care about them. They come from this system of equations. And then I thought, oh, great, I could do the same for the algebra QU. So if you look a little bit at the algebra QU, wait, where is it? Oh, here. You with a little bit more effort, you find that it also has some 2 by 2 representation. Okay? Furthermore, the algebra is 4-dimensional, and 2 by 2 matrices are, the space of 2 by 2 matrices is 4-dimensional. So generically, so if the parameters are generic, it's going to be a faithful representation. So you do exactly the same for QU, and you get a formula for a new lambda. Maybe instead of lambda, call it Q lambda or lambda sub Q, and you get a very similar formula, and then you test it, because we know how to compose. We still don't really know, but we basically you compose generating functions using the rules we know, but we haven't finished developing the techniques, but in principle we know how to do it. So you compose and check if the result is associative, and it isn't. So you fail. So the technique must be broken, because if it works for CU and not for QU, then something must be broken. Okay? And it's broken because this is really half a proof. And here is how this is half a proof. Well, I lied to you about the matrix being faithful. Sorry, about the representation being faithful. It's a faithful representation of the Lie algebra of G. In our case, it's SL2 plus epsilon. But our algebra is CU. It's the universal enveloping algebra. The universal enveloping algebra is infinite dimensional. There is no chance rho will be faithful. Right? If it's on a four-dimensional thing, it could be injective, but on an infinite dimensional thing, it's not going to be injective. So, not quite faithful is the right phrase. Okay? So, but nevertheless, this is the correct answer. So, why is it the correct answer? It's the correct answer because it's not faithful, so the rho we wrote there, rho is not faithful, meaning not one-to-one, on all of CU, but yes faithful on a small subset of CU, and everything that we do happens in that small subset. Okay? And if you switch to QU, then we're not in that small subset, and you don't have faithfulness. So, so it is yes faithful on so-called group-like elements. And what are group-like elements? So group-like elements is the same as exponentials of Lie elements. So these are exponentials of elements in the Lie algebra. So I owe you some proofs. First of all, why is this thing a group-like element? It's not an exponential. It's the product of of 8 exponentials. So I owe you a proof that if you multiply exponentials, the result is an exponential. Well, of course, it's true in the commutative case, but we're not in the commutative case. Likewise for the right-hand side. So I owe you a proof that the product of exponentials is an exponential. Okay? This is the so-called BCH form, BCH theorem, Baker-Campbell-Hausdorff theorem, and at least Jessica had seen a lot of it. Okay? But it's a non-trivial theorem. It's not at all obvious that in the universal enveloping algebra of a Lie algebra, the product of two exponentials is again an exponential. Or not to mention the product of 8. Okay. This was supposed to take about 2 minutes. And now we and now we can actually deal with BCH. So you see, so I could spend some time proving the Bch theorem as is. But I think I want to put it in a slightly wider context. Hence, our chances of reaching the overall goal are shrinking even more. Okay? But here is the more general context. So suppose HC is a co-commutative co-algebra. So co-algebra means that it has epsilon and a coproduct, and co-commutative means that the dual property of commutative. The dual, okay? So basically it means if you take any elements of C, let's call it lowercase c, and apply to it, let's put it in tensor factor I, and apply to it the coproduct which maps I to jk, then this is equal to Ci applied coproduct I kj. Or if you, so flipping the two tensor factors. Or if you wanted to write it in more standard notation, I would write the following. So you have the map C, you have the algebra C, you have the coproduct mapping it into C tensor C, you have again the coproduct mapping it into C tensor C, and you have the permutation map that maps this and C tensor C to that one. So this is the transposition, and to say that the coalgebra is co-commutative is to say that this commutes. Again, if you reverse all the arrows, then this becomes the commutativity of multiplications. So it makes sense. In a co-commutative algebra, in a general co-commutative algebra, I will define two classes of elements. So, definition, an element X inside C is primitive if the coproduct of X is equal to X tensor 1 plus 1 tensor X. And an element uppercase X inside C is called group-like if the coproduct of X is equal to X tensor X. Okay? And my goal is to study primitive and group-like elements in, my next goal is to study primitives and group-likes in the universal enveloping algebra of Lie algebra. Oh, I should have told you the universal enveloping algebra of Lie algebra is automatically, if you look at the formulas for the coproducts, they are co-commutative. So, which is co-commutative. And I think I'm out of time. Yeah, I'm out of time. So this will happen next time, but the conclusion will be, well, group-like elements will be exactly these exponentials, and they will be sorry, they will be the exponentials of primitives. The primitives will be the elements of the Lie algebra, and we will be able to show that the product of group-like elements is group-like. Okay. So see you on Friday.